Potential energy problem, example 1. Let's consider the potential energy, more specifically the electric potential energy, stored between the proton and electron in a hydrogen atom. So we're looking at a proton in the middle and an electron whizzing around it in what I'm going to lie to you and say is a circular trajectory. It's actually not a circular trajectory, but for the sake of this problem, that's what we're going to do. Okay. That's why in the parenthetical below I say this model does not take into consideration the wave nature of the electron itself and only considers the electron to be a particle in circular motion around the proton nucleus. Okay. So we're dealing with an approximation of what really happens in a hydrogen atom. Finally, the second sentence. For a hydrogen atom, the electron and proton are approximately 5.3 times 10 to the negative 11 meters from each other. That's going to be our distance r here. 5.3 times 10 to the negative 11 meters. Very small distance as the electron orbits the proton. How much potential energy is stored between these subatomic particles? This actually ends up being a straightforward problem. As long as we keep with the electric potential energy between two charged particles is K, Coulomb's constant, Q1, which will be charge of the proton, Q2, which will be the charge of the electron, divided by the distance between them, r, which is that distance over there, then we can determine the stored energy. Coulomb's constant approximates to 9e9 in SI units. Charge of the proton is 1.6 times 10 to the negative 19 coulombs, and that's the exact same charge for the electron, except it's equal and opposite. Squared, and a negative will pop out. Next, for the denominator, it is this 5.3 times 10 to the negative 11 meters. I did everything in SI units, is why I didn't explicitly write out my units, but everything here is in SI units. For example, this Coulomb's constant can be written in joules meters per coulomb squared, and that's an appropriate unit for that, 9e9. The two charges were in coulombs, and the distance is in meters. Throwing this in my calculator, 9e9 times 1.6e negative 19 squared divided by 5.3e negative 11. I get a small amount of energy. That is going to be 4.3, I'm going to round that to 5, e negative 18 joules. Okay, that's the electric potential energy stored. Many times, instead of seeing this in joules, you'll see this in electron volts. What's an electron volt? Well, a joule is equal to the charge of an electron multiplied by the voltage. These are not exactly equivalent units. This would be 1 coulomb, multiply that. So what's this charge of an electron going on here? That has to do with it being a charge of an electron being 1.6 times 10 to the negative 19 coulombs. So they're not exactly equal to each other. So to make them equal, I actually have to divide whatever's over here to that. So what is the same answer in electron volts? It will be electric potential energy will be equal to that 4.35 e negative 18 joules divided by 1.6 e negative 19, which gives me 27.1 or 2 electron volts. And I forgot my negative earlier. Boom. Okay. There we go. That is the two different ways that you can determine the energy stored between the electron and proton in a standard hydrogen atom. It's not the last thing that was asked for. There's a little bonus thing here. Also, what is the kinetic energy of the electron going around the proton? This is actually a much more difficult problem because I'm going to assume that the proton is stationary, which is fine for approximation reasons. The proton is so much larger in mass than the electron that it's actually a reasonable assumption. So the kinetic energy, if the proton's not moving, will just be equal to 1/2 mass of the electron multiplied by the speed of the electron squared. We don't have the speed of the electron, kind of. It's very similar to, it's why I included the statement about the circular motion. How does that help us? It helps us because of forces. The electron is going in circular motion because it has an inwards net force. That's completely and only due to this electric interaction between the two. I can approximate these as being point charges. So I can say the Coulomb attraction is equal to mv squared over r. Clean that up. Where'd this come from? This is because we're dealing with circular motion. That's the centripetal acceleration, and this is our only force that we're worried about. We don't worry about gravity because it's minuscule. Taking this, I can solve for v squared. V squared is equal to Coulomb force times the radius divided by the mass of the electron. Taking this, I can plug that in for here. My kinetic energy is now equal to 1/2 mass of the electron times the Coulomb force multiplied by the radius of motion divided by the mass of the electron. Boink, boink. I'm actually not going to be doing many calculations because this is going to clean up very nicely. Substituting in for the force, the Coulomb force, the 1/2 stays the same. Coulomb's force is Coulomb's constant. The two charges being considered, QP, QE, divided by the radius squared, and then multiplied by this radius as well, which causes a single cancellation. There's one more aspect. There's a inwards-outwards consideration. This over here is supposed to be inwards, so it needed to be in the negative r hat direction. So there's a negative sign that should have propagated in here. I'm going to make this magnitude just for, so I don't have to worry about negative signs. Just whatever would have been in there, going to get that negative out of there. Boom. get 1/2 K, charge of the proton, magnitude of the charge of the electron, divided by the radius. This we've seen already. This we've calculated already. It's exactly this. So what is going to be the kinetic energy? The kinetic energy is going to be 1/2 of the magnitude of the electric potential energy. Therefore, the kinetic energy is going to be equal to half of this or half of this, your choice of units. So that will be divided by 2. So 4.35 times 10 to the negative 18 gives me 2.17 times 10 to the negative 18 joules. Or if I do the same thing in dark green, I can get 27.2 EV divided by 2, giving me 13.6 EV. This is a nice, interesting result where if you have nice, clean circular motion, only works for circular motion because we had to use this consideration here, then the kinetic energy is equal to half the magnitude of the potential energy in circular motion. Where only one object moving. The center one is stationary. I call that orbiting in circular motion. Then the kinetic energy of the one in orbit is equal to 1/2 of the magnitude of the potential energy in that system of the pair. This happens in circular motion for planets as well, as long as we're considering the circular motion of one of the planets compared to, say, the sun, or the kinetic energy of the moon relative to the Earth-Moon potential energy. Big takeaway right there. There's example problem number 1.